I'll lead off.
Yeah, I'll just say what we're going to do very briefly. So, thanks for coming. We're going to run through climate science. If stuff is really obvious to you, and you think you all know it, you can interrupt us and tell us that. If there's stuff you don't understand, you can interrupt us and go along and ask questions. Gaia is going to cover the basic science of it, including the physics, and I'm going to talk about some of the implications, scenarios, and adaptation.
Okay, so thank you folks for your attendance today. I'll just give you a very short potted history of my background to give you some context to why I might not be a bad guy to have this conversation. I set up a little consulting firm in 2002 called CO2, SEAO2, and one of my first clients was the Commonwealth Government for a program in Australia called the Greenhouse Challenge. And my job in that was to visit companies, factories and farms and marine tourism operations, and to conduct carbon audits to assess how much greenhouse gas they produced and advise how they might reduce their greenhouse gases. And that led to a broader interest in climate change, and so I read a lot, and then I had a program with the Townsville City Council where I ran a 4-hour workshop for all of the new recruits that covered off a whole suite of sustainability issues, a large part of which was climate. So I've been reading this stuff for over 20 years. And as you read it over and over and over, it gets a little bit sort of, so I started drilling down into some of the sort of more obscure and abstract aspects of climate science. And so one of the things that I do is I help people get their head around this thing. What I want to do is firstly is to talk about where the scientific understanding of climate came from, and to draw upon the work of Jean-Baptiste Fourier, who in the 1820s or thereabouts put together a science paper, and he referred to the bell jar hypothesis. If you remember from high school science, a bell jar is basically a glass jar like that, and you put things inside it. And what he was saying was that what we observed was if sunlight fell upon the bell jar, then the inside warmed up more than the outside air. And there was the analogy that something's happening in the atmosphere, or the gas around the Earth, that is trapping heat. And the observation was, I think it's actually French, and so the observation was, if the depths of space is icy cold, how can it be warm on a winter's night? There's something going on with the planet. And then later on, some scientists, I think Tyndall as one of them, Tyndall, identified that there were specific gases in the atmosphere that were actually absorbing and holding on to the heat. In particular, they found carbon dioxide and methane and nitrous oxide, and they started to actually analyze the capacity of each of these gases to absorb and hold on to the heat. And that was really the beginnings of starting to understand the mechanisms, if you like, by which the planet was kept warm. And then later on, there was a character by the name of Savant Horinus, who in 1896 put out calculations where he basically calculated the single climate sensitivity, which is a really important scientific principle around climate change, which is if you double the amount of these warming gases, how much hotter does the planet get? And he wrote this treatise out by, there's no computers or calculators back in those days, wrote it all out by hand, and he came up with numbers which are consistent with that we see from supercomputer modeling. So it sort of says that this science has been around a few hundred years, and that it's kind of pretty basic stuff. It's well understood that the basic physics is very well understood.
Would you write the names of,
Yeah.
I've got Tyndall in the middle, but I don't
Yeah.
get the first or the third.
Fourier, F-O-U-R-I-E-R, Jean-Baptiste. Famous also for a thing called the Fourier transform, which electrical engineers use, I think, sort of on a daily basis, which allows you to look at a complex signal and break it down into simpler parts. Very important piece of engineering. So every time, if I ever meet somebody who argues, an engineer who argues about climate science, I say, well, you trust Fourier on the transform, but you don't trust him on the bell jar hypothesis. The joke's on you. The other guy was Tyndall. And Svante are blurriness. Okay, there's one other person in there's lots of other people in the scientific journey. I'm just trying to whoosh through it. Another fellow called Callender, Joseph or John Callender. He was commissioned by the American military to assess the impact of using nukes against Russian shipping. And one of the things they wanted to figure out was whether it would leave this terrible radioactive decay that would destroy the whole ocean. And what Callender found was that there is this stratification in the ocean, that the surface waters don't mix well with the lower waters. And what he concluded from that also was that the radioactive contamination would stay thick at the top rather than being perfectly diluted. But what he also sort of discovered was, and this is important stuff, is that it had been established that these gases, particularly CO2, methane and nitrous oxide, but particularly CO2, because I'll explain why, but that was coming out of industry and burning fossil fuels, coal particularly back in those days, was building up in the atmosphere, so therefore potentially heating the planet, but the consideration was it was all being sucked up into the ocean, so don't worry about it. And what Callender found was that indeed the ocean didn't suck everything up completely, but it sort of stratified it at the top. And this was sort of in the 50s, and it was the beginnings of the world actually kind of getting its head around like the implications of what was now a global civilization powered by fossil fuels. And it was in the 50s, I think around 57, that the World Meteorological Organization in one of their big gatherings actually used the term climate change as a threat to humanity. So it goes back a way that we've been talking about this stuff and doing nothing about it. I want to just draw a couple of little diagrams. I want you to imagine that this thing here is planet Earth, okay, and this thing up here is the atmosphere. Now the atmosphere, of course, is made up of, I actually had the number, I've got the number in my little book, Vita Awakening. It's something in the order of 17 hectodecatrillion air molecules in the atmosphere. So molecule theory, or the theory of gases, is that as we stand here, my eyeballs are being bombarded by 200 trillion tiny particles every second, traveling at about 250 kilometers an hour on average. The surrounding us is a ball, surrounding our planet is a ball of gas which is comprised of little molecules which exist in the gas form, which is to say that they're not kind of connected to things, they're actually just like flying all over the place. As they strike surfaces, they just bounce off into a different direction. And that what there exists on the planet Earth, where we are standing right now, is the vacuum of space plus air molecules. And that in between each of these tiny molecules, there is the vacuum of space. I think that's for me, that's something that touches me eco-spiritually somehow. We're actually in space without a helmet. The ball of gas is our spacesuit, sort of thing. So as these things are flying around the place, I think at 25 degrees Celsius, I think the average speed of the CO2 molecule is about 230 kilometers an hour. That's an average. They can go much faster, but when they bang into another molecule, they can actually stop dead, all right? And they're kind of suspended in this void of gravity. Doesn't affect them so much because they're moving so much. There's more of them at the ground level than there is up in the air. If you hear about the edge of space, often that's referred to as 100 kilometers, which is called the Kármán line, which is actually the line beyond which planes that rely on aerodynamic lift can't function, because there's simply not enough air molecules. Thick down the bottom, less at the top. The edge of space is, say, 100 kilometers, but in reality there's air molecules out a few thousand kilometers, but so few of them that it's barely mentioning. The International Space Station, which cruises around the planet about 400 and something kilometers, is affected a small amount by the little traces of air molecules, and periodically they got to like just boost it to overcome. But most of the other molecules are down on the ground, and it's sort of the gravitational force bringing them close to the ground. Okay. I'll come back to this diagram in a minute, but this is important stuff. If you were to have a volume of air, then 78%, what's that? It's 75, so 78% is a gas called nitrogen. that exists in a bond with another, so two nitrogen atoms joined together, very, very stable, flying around, right? 78% of the gas is nitrogen gas. 21% in here is O2, so this is oxygen, that's what we breathe for. That's the chemical that we use to drive our metabolism. This is just like the filler, and the remaining 1% is a whole mixed bag of gases. They're called trace gases. Actually, tell you a lie, there's a 0.8 in there. 0.8% is ozone, and so that means the remaining 0.2 is all the traces, and that includes our friend CO2, CH4, which is methane, and N2O, which are the main naturally occurring greenhouse gases. I'll explain what greenhouse gases means in a minute. Then there's a whole bunch of other stuff down here which is not relevant to our conversation. These creatures, or these fellas here, make up a tiny fraction of the air around us, and yet have a profound impact on making this planet livable. Because if there was no greenhouse gases in the atmosphere, if these didn't exist in our atmosphere, then I want you to imagine that I need a full-time board cleaner.
The contrast class is the moon, the obvious one, right?
Yeah.
So the temperature on the moon is like 40 degrees less than here.
Okay, so let's make some distinctions. Here's the moon, using an example of a planet that doesn't have an atmosphere. On the sunlit side, okay, it's I think around 210 Celsius or something. It's very, very hot. But on the dark side, the side that doesn't have the sun, it's down around -200 or something. Okay, and so what if you then were to hypothetically, let's say for example that we've got planet Earth with no greenhouse gases, then it's going to be baking hot on one side, freezing cold on the other, and you're going to have a 200 plus 300 degree Celsius temperature change at dusk.
Say that again, please.
Um,
You will have.
If there were no greenhouse-
I got it all. What's the percentage of that shift?
What I'm saying is sort of it's 180 or something Celsius negative and about the same in positive. That's
You sure that's right? You're not thinking of Mercury?
I'm talking about the sunlit side is illuminated and heated by the sun.
Yeah.
It's very hot.
Mm.
Okay, and the other side is extremely cold. I'm not going to hang myself on these numbers, except to say that there would be this massive temperature difference as the sun went down, and trying to conduct living things. Well, given that if it goes into the negative 100 degrees Celsius, there's nothing that's going to live because it's so freaking cold. There's no liquid water. And this is one of the principles of life on Earth: is the abundance of liquid water, because temperatures and pressures allow us to have liquid water, gaseous water, water vapor in the atmosphere, and ice. Those three things, the conditions on Earth are suited to those three forms of water, and that's why we've got living things here. Okay, so here's the thing. If we were to then look at our planet and the ball of gas around the outside of it with these tiny traces of the greenhouse gases, what we are doing to the planet in the exploitation of coal, oil and gas is we are extracting material from the Earth's crust where it is not associated with the atmosphere in the form of coal, oil and gas, and we are burning it, and as we burn it, it releases water vapor and it releases CO2. Now water vapor and CO2 are both greenhouse gases. Water vapor is treated separately generally for reasons I'll go into maybe. And so if you can imagine that what we've got in these coal fields, or the gas, or the petrol, or the diesel, or the bunker fuel, or the aviation fuel, or the kerosene, aviation fuel, or the petroleum wax candles, ladies.
Or the cows, no?
Yes, I'm talking specifically about CO2. I'm talking about fossil fuels. We'll come to the cows in a minute. What you've actually got in the fossil fuels is a molecule, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17. This is called a hydrocarbon molecule, and broadly speaking, all of the fossil fuels are hydrocarbons. Methane, which is the one that comes out of the back of the cow, actually mostly out of the front of the cow, comes from the forward thing, is CH4. So molecularly, it looks like this. It's a carbon molecule with 4 hydrogens. But if you go and look at something like petrol, it's effectively, this is a very simplistic diagram. It's basically a chain of carbons surrounded by hydrogen atoms. And when you run that into an internal combustion engine, which is what we silly people do so much, then exposed to the abundance of O2 in the atmosphere, okay, O2, 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 when you put this thing under pressure and you heat it, it breaks apart and the H's and the O's and the C's reform, okay, to create an abundance of that and an abundance of that, okay? Also a greenhouse gas, but we'll just discard it for a few minutes for various reasons. This is the main concern, is that when you burn these things, you get an abundance of this, CO2. Wonderful stuff. It's plant food. Plants love it. That's how you grow life on Earth. You've got to have some CO2. And the temperature of the planet and the concentration of CO2, as well as the other greenhouse gases, but predominantly CO2, has sort of, generally speaking, gone up and down together for eons, at least in the last 3, 4, 5 million years that the human species has been around in any form, okay? And so this is the concern, that as you put more and more of the CO2 into the atmosphere, it absorbs, holds on to more heat. It makes the planet, on average, hotter. Now, when I say the planet hotter, something in the order of 93%. Come back to that. Firstly, equipartition theory. So, why is it that the greenhouse gases have this relationship with heat? That's the principle. Okay, let's do that. This is one of the little arcane areas of climate science that I find fascinating, and I'm not going to go into the detail because it would do your head in. But there's a thing called equipartition theory, which helps to explain how molecules absorb heat, right? So what you've got playing out on the planet Earth is we've got the sun over here, and the sun is sending out short wave radiation, white light, okay? If that white light from the sun strikes the top of a cloud, it sort of goes and sort of reflects, almost perfect mirror, back into space. This is called the albedo effect, and not to be mistaken for the libido effect, which is very different indeed, Rupert. Okay, so if the the short wave radiation, like shortwave radiation, strikes a white surface, it bounces off into space. But if it comes down here and strikes, say for example, a leaf of a tree, a dark surface, then what happens is that shortwave radiation, it turns into warmth. You know that when you go outside and you feel the sun on your skin, that energy from the sun has come across 150 million kilometers, uninterrupted because it's come through space, uninterrupted because it comes through the atmosphere, and there's nothing in the atmosphere that will trap the shortwave radiation, okay? But when it strikes the leaf or the roof of the car or the black surface of the road, the darker it is, the more likely you're going to get this thing turn into warmth, right? Or heat, okay? Or infrared radiation, which is the proper kind of terminology, infrared. This is all about the electromagnetic spectrum. We won't go into that. The darker this is, the more heat will be created, and the lighter it is, the less, because if it's really white, it will just basically reflect off like a mirror, okay? Then the warmth radiates out in the form we call long wave radiation. So you can go into all the nanometers and all of the technical stuff. The short wave comes from the sun, that reflects off white surfaces and goes away, doesn't cause a problem, and isn't interfered with by air molecules, any of them. But the long wave radiation is what is affected, or is what affects the greenhouse gases, okay? And this is the little equipartition theory bit, and to just explain this because it's kind of if you get hit around this little bit, so much becomes clear. The CO2 molecule looks effectively like this. It's 3 molecules in a row. You've got your C and you've got your O's on the outside, right? CO2, C, 1, 2 O's, oxygens. As the long-wave radiation, long-wave radiation, just think of a hose watering the garden. It comes out in a long stream. That's not how energy moves in the universe. This is Einstein stuff. This is quantum theory, okay? Energy moves, electromagnetic energy, moves in little packets called quanta, all right? Little packets called quanta. So where I've got a line here, in reality, it should sort of look like that, okay? So it's little packets, links. And in this case, these little packets are little packets of infrared radiation or just heat radiating out, radiating from the warm surface of the planet. Now, when the old CO2 molecule is exposed to these infrared radiation, these little quanta, these little packets of energy, heat energy, what happens is that it starts to make vibrations. It's got 3 forms of kinetic energy, right? This is a partition. The one form of kinetic energy is the little packets of heat make it go faster. Okay, it's called translational energy. It simply moves faster in the presence of this warmth. The other thing it does is it actually spins like this, like end over end, like this. Okay, and the other thing it does is the distance between the molecules opens and closes like that. In fact, it sort of acts like a little bit like wings on a bird. So what happens is as it absorbs these infrared packets of infrared energy, it starts to go like that. And for every packet of energy, it kind of goes up 1 level. Again, a quantized increase in its overall energy, kinetic energy budget. And what the little CO2 molecule then promptly does is it goes, sends that packet of energy back out again and returns to its lower state, okay? So what happens if you're a CO2 molecule cruising around the place, here's the Earth, here's the tiny packets of long-wave radiation, here's Mr. CO2 molecule, picks one up, goes a little bit excited, and then flips it back out again. It heats up and then cools down. And in so doing, ejects the long-wave radiation, the infrared photon, the infrared photon, which is one of these packets, that's what it's called, an infrared photon of energy. And that is either going to be sent in the direction of the ground, or it's going to be sent in the direction of space, or it's going to be sent over here and bump into an oxygen molecule. And this is what the problem is that these little guys are holding on to, even for a microsecond, and then re-radiating infrared photons. And the bits that head back down like that, or hit these things, which makes these things go faster, which increases the overall temperature, because temperature is the average velocity of the air molecules. So if these things are going faster, or the ejected infrared photon is striking this thing here, that's not actually correct, because these things aren't affected by, these things aren't affected by the infrared photon. But it could eject its infrared photon to another CO2 molecule, okay?
Yeah, and the key thing is that there's enough CO2 molecules that most of this long-wave radiation is going to hit one of them before it gets back out again.
Yeah, and then bounce off. So what's happening is you've got this little thingy that's trapping, holding on for a second and then releasing this energy, which otherwise might have just zipped off into space. And those little infrared photons, whilst they're minuscule in their size, when you multiply them by hundreds of billions of trillions, adds up to a lot of heat on the Earth system. This pushing back down of the energy that would otherwise have disappeared is called radiative forcing, and that's the term you use. It's the scientific term here about radiative forcing has increased by X amount of watts per square meter. Okay, so that's that. Now I just want to go stay on that theme for a second. And if we have a creature called, so let's say we've got the CO2 over here with the 3 dots, and now we've got CH4, which is your methane. There are more ways for that molecule to wiggle because it's got more kind of connections. And as a result, it will accept and hold on to more of the infrared photons, which explains why when we're talking about greenhouse gases, we talk about this thing called global warming potential. Okay, GWP is a way of describing the capacity to hold on and release heat of a greenhouse gas, and CO2 is given the number 1, it's a referential frame. Okay, methane has got a global warming potential around 21, which is to say that a single molecule of methane has got 21 times more capacity to heat the planet. Now, there's levels of detail in that, but I'll just glance across one. You'll often see also that methane is ascribed a global warming potential of 80, and sometimes another number. The distinction, you tend not to see this one having another number. The distinction is that when this stuff goes in the atmosphere, it stays around for a really long time. Okay, it's there for thousands, under natural conditions, it's there for tens of thousands, hundreds of thousands of years. Whereas this one is actually really reactive and bonds with oxygen and does all sorts of things and basically falls apart pretty quickly. It is more warming, it has a greater capacity to heat, but it doesn't last as long. So these two numbers that you'll see relate to it over a 100-year time frame. It's got, over 100 years, it's got 21 units of heating, but over, say, 20 years, it's got a greater amount. Whereas this one, over 100 years versus 20 years, is basically the same. Okay, so that, if you see that and get confused, that's basically this time. There is a molecule called CFC23, chlorofluorocarbon with 23 somethings in it, which has a global warming potential of 23,000, which is to say that one molecule of this stuff has the equivalent heating capacity of 23 tons, or one molecule of 23,000 of those. So when I was saying a ton of this is equal to 23,000 tons of that. And this is manufactured by human beings in factories as part of the producing microchips. And so whilst we talk normally about climate change, we're talking about the CO2, CH4, which is the methane, cows and rice paddies, and comes out of oil fields as well. And fracking, yeah, and N2O, which is nitrous oxide, which comes out of agricultural use of fertilizers. These are natural, but there's a whole raft of these manufactured ones, some of which have got these ridiculously high global warming potentials, and they're not considered in such effect or so much because the quantities of these are minuscule compared to CO2. Just the other day I read that with everything getting back on its feet after COVID, last year, I think the figure was 2021, the humans ejected, what did I say, 36 gigatons of carbon. Is that CO2 or is that C? It doesn't matter. Just get your head around that number. Let's put it another way. 36, 1, 2, 3, 1, 2, 3, 1, 2, 3. Is that a billion? 36 billion?
Yeah.
1,000 million. Okay, tons. That's metric of, say, CO2 of CO2. That's how much CO2 gas humans are putting into the atmosphere. I think it got up to 43 gigatons at one point, but it's come down a bit because of COVID. Probably going to go back up again despite the Paris Agreement. And this is fundamentally what's driving the climate change issue, or let's put it this way, if the extra heating of the planet because of greenhouse gases was to be represented by this chart, then I think in the order of that much is CO2 and this much is to do with methane. Okay, so the global warming problem is predominantly CO2, but a large part also is CH4, which is methane, and then the other greenhouse gases, the heating effect of the other greenhouse gases is in here. This one gets all of the focus because it lasts a very long time in the atmosphere. This one breaks down relatively quickly, so if we stop emitting it, it would basically go back to normal levels relatively quickly. So this is the one that gets all the attention. At this point in time, the humans have ejected around 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 tons CO2. Sorry, it's actually 2. So to this point, humans since the Industrial Revolution have put about 2,000 billion tons of CO2 into the atmosphere. The group that I follow, which is called Climate Restoration, who plans to restore the climate back to the way it was pre-industrial periods by 2050, are saying we need to remove 1 trillion tons of CO2 from the atmosphere. Because around half of all the greenhouse gas that's been put up into the atmosphere has been taken up by plants and soils and by the ocean, which has got its own problem.
What's that group called again? You follow?
Climate restoration. Okay, so prior to the Industrial Revolution, say around, you tell me when, okay, I'll speak for another 3-4 minutes. Prior to, say, 1750, beginning of the Industrial Revolution, widespread use of coal, the amount of CO2 in the atmosphere was around 275 parts per million, is how it's measured, okay? If you had a cage full of 10,000 ping pong balls, 3 of them, less than 3, would be painted red. That would represent the CO2 in the atmosphere, to give you an idea of how little of it there is in the atmosphere. Since 1750 up to today, so where we are now 2022, we now have 416 parts per million. That is kind of the problem. In a way, the 34 gigatons that we put into the atmosphere is problematical, but it's kind of not the problem. The problem is this vast amount of gas that's up there already, because that's what's doing the radiating forcing and heating the planet.
It's cumulative, in other words.
The cumulative.
Because it stays up there so long.
So you've gone from
that's
a
right.
spring duvet to a winter duvet.
And the winter duvet is always on.
Yeah. Okay, so
Do we know, I don't know if it's the right question, but do we know how much the capacity of absorption of, as you said, like plant, ocean?
yeah, it's saturated. Saturated.
So it can't anymore absorb, or does every year there is still an absorption?
Around 25% of the greenhouse gas that the humans eject gets absorbed through natural processes into the ocean. The problem with that is that when you add CO2 to water, you get carbonic acid, right? Which is like what you take if you drink Coke, soft drinks. So yeah, we can keep ejecting CO2 in the atmosphere and it can keep getting absorbed into the ocean, but ocean acidification is annihilating wildlife, okay? Around 25%, I mean these are round numbers, goes into forests and into soils. But again, there's a certain point beyond which the plants aren't, so the plants are evolved to live in an environment of 275 parts per million. If we keep adding and adding and adding, what it does is it tends to actually benefit the fast-growing weedy plants and not so much the ones that actually hold on to the carbon. And there's also issues around soil carbon. So at some point, what humanity needs to do, and it should have started this back in the 50s when we realised the problem, is to find means to pull this CO2 out of the atmosphere, just get it out of the atmosphere.
And do we already have means to do that, or are there ideas circulating around?
Yeah, and this is a huge, the climate restoration mob has spent a lot of time on this. The simplest way is to foster the growth of organic material, because as you grow things, you know, everything's based on green cells, photosynthesis, carbon dioxide, all then turned into sugars, turned into the bodies of plants. So growing forests, restoring soils, massive opportunity is to have soil carbon, which is really basically just organic material in soil. So you take sand and it turns into a nice loam, if you like. The growth of phytoplankton is another one that they're looking at. You can foster the growth of phytoplankton, and as they grow, they absorb CO2 and their carcasses fall to the seafloor and effectively move carbon from the atmosphere down to the seafloor where it's no longer a climate threat, it's a natural process. And there are these chemical processes as well. So the climate restoration people have tied in with this group that have got a chemical process, which is the same chemical process that coral uses to grow, which is calcium carbonate. It's also pulls carbon out of water, and they're using it to make road base. Road base is the gravel stuff that they use, they make a road out of, right? The reason that they're interested in that is because road base is the only material which is used on the scale of tens of billions of tons a year. So if they can say to the world, stop using gravel, start using this stuff, and we can pull the carbon out and build roads out of it, right? I think that's a pretty good.
Yeah, just to add briefly to that, we could spend a lot of time talking about that. There are concerns about most of these schemes, especially when they're done at a large scale, quickly, industrially, etc.
Yeah.
So it's not as simple as, oh well, let's just have lots of nice new forests or something.
Yeah.
One particular cause of concern around forests is that, and this is very tragic to contemplate, because we're very, very probably going to have significant further increases in temperature and crazy weather in the next few decades. It's highly likely that many of the forests that are planted, as well as many of the forests that already are going to burn. So an example of that is Microsoft has been saying for the last few years, you know, we're going carbon neutral, etc. So Microsoft has created all these forests in California and the west coast of America until last summer, where they disappeared.
Yeah.
And when it's not cut, simply cut in Europe, we have in Poland, and the
Yes,
business,
yeah.
they're cutting more and more and more.
Yeah, and that's a lot to do with the drive for biofuels, which is another potential problem rather than solution.
Yeah. Can I just finish on one more thing? Just one more quick thing and then jump over. The climate change problem is, or the solution, if you like, to the climate change problem is, in the UN sense, is to reduce greenhouse gas emissions by transferring away from fossil fuels and to use renewable energy. There's problems there. But there's actually only one of three problems, okay? The one problem is that we've got too much, 416 ppm, we've got too much of the greenhouse gas in the atmosphere. That's problem number one, right? We've got 1 trillion tons of excess heat trapping gas. Problem number one, okay? So theoretically, what the UN's proposal to do is to stop making that worse.
Yeah.
Because, right? The second problem, okay, is that, so firstly, the first challenge is to stop making it worse, which is the transition to clean energy, which has got a huge carbon footprint because you've got to build the windmills out of something. The second thing is that we've got all this excess gas, right? Okay, which is the extra 1 trillion tons, which is the whole drawdown thing. But the third problem, and this is the one that's really tricky, is that we've got this massive buildup of heat that's already in the system that shouldn't be there. Most of the heat that's been absorbed by the CO2 has gone into the oceans. The oceans are warmer, and that's what's leading to the meltdown of the underside of the Arctic, of the Antarctic, the ice sheets, and particularly the Arctic region, because the Arctic region is supposed to be white. And you remember my story that the sunlight reflects off the albedo, but if it's not white because the ocean is warmer and the ice is melting, then you get more heat coming in. So the big problem, and this is the one that's tricky, is somehow dealing with all this excess heat. And the solution to that is called solar radiation management, which is around putting up mechanisms to have more white stuff in the sky. And that's a whole can of worms right there.
Yeah.
Okay.
Did you have something before I go?
Yeah, no, it's self-perpetuating, isn't it? Because we're one of the heating systems, so the 1 trillion is not 1 trillion. It's actually more than 1 trillion by a long shot. So we need to go to negative.
Yeah.
So
Well, we need to go back to 275 parts per million.
but even at this, no, there's still a legacy, there's still a lag on the 1 trillion.
Yeah.
The 416's got its own energy.
Yeah.
So it's going to self-perpetuate and get worse.
Okay.
Okay, so Guy's given you a lot.
Can we just stretch our bodies?
Yeah.
Thank you. You stretch bodies if you need to before we start again.
We're probably get 500 before we do.
But, oh well, yeah.
Water so that
416
we
now.
can give you our full attention. Thank you. Appreciate that.
Is Valerie coming back, I guess, or?
Probably.
Assume so. She's left something, hasn't she?
Yeah. She probably went to the restroom.
While we're waiting, it's 25% forests, 25% oceans. We've got 50% legacy. Where does that go?
Yeah.
So that's what building up the additional BPM.
Mm-hmm.
Okay.
So,
Round two.
I have another question about, you said that, they want to use from what corals used and to put that on the streets, so that would also then have a white surface, right?
It would go under the tongue. It's the base. It's the material that builds up from the ground
But
up.
are we also starting to have white streets instead of?
Yeah, and that's one of the ways of helping cities to become cooler is to paint many surfaces white.
Yeah.
Roofs as well.
Yeah.
Particularly
Roofs are kind of better than roads because, you know, a road's really going to stay white.
Yeah,
Skeptical.
black tiles.
Okay, guys, giving you a lot. I'll seek to be briefer. So, who am I? What's my credentials for this? So, I'm an eco-philosopher. I work alongside some of the world's leading climate scientists at the University of East Anglia. I publish mainly these days on the implications of climate and ecological science. And I'm an expert reviewer for the IPCC Working Group 2. So the IPCC is the International Panel on Climate Change. Intergovernmental Panel on Climate Change. Scientists, academics working for governments and for the UN, essentially. And I'm a reviewer of Working Group 2 of that. There are 3 working groups, 1, 2 and 3. 1 is basically the physical climate science, the kind of stuff that guys will talk with you about. 2 is about vulnerability and adaptation. That was the one that got published very recently, which is the scariest IPCC report yet. And 3 is basically on policy, what to do about it. And I can let you into a little secret, right, if you don't post this up on YouTube for next week.
Oh, it's going to go up this afternoon, so.
Right. All right, I won't let you into that secret. Yeah, I'll say that this right now, they're producing a new one of these right now, this week and this weekend. It's proving pretty difficult to get agreement on it. I haven't seen any more than that on camera. The IPCC historically has been quite cautious. By cautious, I mean they've been careful to preserve their scientific reputations. They take a long time to produce their reports. They're always therefore behind the curve. They don't want to antagonize governments too much. Governments can edit the summaries of IPCC reports. So, and the summaries mostly is just what anybody, hardly anyone reads the actual full reports. So what you get from the IPCC in various ways is actually tends to be behind the curve. So if you ever hear, they don't do it so much anymore, but climate skeptics, so-called, used to attack the IPCC and say, oh, they're scaremongering, it's alarmism. It's the opposite. The IPCC are telling you like the best possible scenario most of the time, rather than the worst possible scenario. But the IPCC have been gradually catching up to where things really are. And the latest report from Working Group 2 is, I think, the best yet. And as I just implied, the Working Group 3 report coming out, if it's allowed to fully come out, will be quite dramatic. What are these elements of the IPCC and governments through the Paris process, etc.? What are they trying to do? What are the different aspects of policy, etc., with regard to climate? So it can be broken down into the following categories, roughly: prevention, mitigation, adaptation, and loss and damage. These are not perfect terms by any means, but these are the technical terms that are used, so I'm explaining them. Prevention, well, that means not creating the problem in the first place. So in some fairly obvious sense, it's too late for prevention. Mitigation means reducing the amount of greenhouse gas in the atmosphere, basically. And that's where most of the focus has been to date. As you're probably already aware from stuff of mine you've seen, I believe there now needs to be a lot more focus on adaptation because it's too late for a focus only on prevention and mitigation. What kind of focus one has on adaptation is a crucial question. I'll say something about that in a second. The focus on adaptation is now gradually increasing. It's getting a bit more serious, but it still lags a long way behind the interest in so-called mitigation. There are reasons for that. One reason is because, in my belief, once you start taking adaptation seriously, you can't deny that the problem is real. Whereas there's a kind of soft denial in saying, well, it's all about mitigation, it's all about getting to 2050 and by that time we'll have reduced the amount down to zero that we're adding to the atmosphere. No, we're already in the era of climate chaos since about 2016. It's too late to think that way, but people don't want to accept that, so they carry on talking endlessly about mitigation. And this applies to a lot of activists.
And the last sentence again.
This applies to a lot of activists. A lot of activists don't want to think we're in the shit. It's you know, people are going to really suffer and die and so on. They want to cut off the problem at source, but it's too late to cut off the problem at source. It's too late to do that alone. And then loss and damage is what happens when it's really too late and you've actually got serious stuff which has been smashed up and needs to be repaired, etc. At COP26 at Glasgow, for the first time, there was a sort of serious discussion of loss and damage, which is good. But there still wasn't, in my view, nearly enough discussion of, let alone action on adaptation. And that brings us perhaps to the second reason why there tends to be less focus on adaptation than on mitigation, which is that mitigation is something which is a kind of gesture for the long-term good of humanity and for the good of everybody, because the climate problem is a genuinely global problem. So it's a wonderful sort of public-spirited thing to do. So you'd think, well, given that adaptation is about people helping themselves cope with what's here and now, surely it would be humanly natural for humans to do a lot more adaptation, a lot less mitigation. But actually, if you can get other people to do mitigation, that's good for you and for your descendants. So if you look at where the money is going from the rich countries to the poor countries, insofar as any is going, it's mostly going on mitigation, which will eventually help the rich countries, rather than adaptation, which would be for the benefit of the poorer countries. So that's a kind of brutal, politically explosive reason why actually most of the effort and interest and money still goes on mitigation. So the danger that I think climate activists play into when they focus on mitigation so much is that they're actually playing the game of the rich companies and the big corporations, etc. And what should adaptation mean? How should we cope with what is coming, which, as I've implied already, is likely to be, if anything, worse, perhaps much worse than what the IPCC has said, even in the most recent report, which was pretty good. So we can distinguish between different varieties of adaptation. I'll be talking a bit about this next week in our evening sessions. So just very briefly now, the key distinction that I'll be talking about what I call spiritual adaptation and also about deep adaptation. But in terms of the way this starts to hit in terms of government policy, it's more to do with things like infrastructure and so forth. And we can make a basic distinction between forms of adaptation which are essentially defensive, things like building higher flood defences, and forms of adaptation that are transformative, that actually change the way that we live and could help to contribute to solving the problem at source. And
what was the defensive example you gave?
Things like higher sea walls. Yeah, basically defensive adaptation tries to keep the show on the road. And in that sense, if you only do defensive adaptation, it can actually be worse than nothing. That's, for example, Australian government policy essentially, is to say they've moved straight from climate denial to it's too late to do anything about it, we have to adapt. And what they mean by adapt is defensive adaptation, which just enables them to keep going a bit longer as they are. So this is a pretty stark, really important difference. And in my view, the struggle to define adaptation is in many ways going to be the defining struggle of the next decade. I would put it as strongly as that. And that's one reason why it's important to consider all aspects of this, including the stuff that we'll be talking about next week. How to do adaptation psychologically, spiritually, collectively. Okay, I just want to make two more points and then over to you for questions and discussion. One point is to say that as Guy started to touch on towards the end of his remarks, if we're really going to think about all of this adequately, we can't think about it just as a problem of sort of physical science. We have to think about it also as how it affects human society and what we do about it. But also, it's not just about physical science in the sense of physics and chemistry in the first place. It's also about biology and ecology. And we're coming to understand this better and better. The way that life on Earth makes a huge difference to the climate issue throughout. So here's an example. They found in recent years that there is some quite substantial sequestering of carbon going on through the bodies of whales and dolphins that sink to the bottom of the ocean because they're so fucking big, right? Basically, right? But guess what? We've killed most of them, so it's not happening anymore. So there's a huge chunk of carbon that could have been sunk and no longer be a problem, which has now escaped into the system and out of the atmosphere again. Similarly, in relation to fishing, extraordinary studies in recent years suggesting that fishing, in terms of the depletion of fish stocks, is an enormous contribution to overheating. But when I say enormous, I mean it may be comparable to the problem caused by fossil fuels. Let me just say that again. A study a couple of years ago suggested that it's possible that the amount of the problem that we have in relation to climate from overfishing may be about the same as the amount we have from carbon and stuff in the atmosphere. Absolutely humongously huge. Again, it's the same kind of set of basic ideas, but it's also to do with maintaining a healthy ecosystem, the plankton, etc. So that's one part of it. Which should be very important to us, I think, from a broadly eco-spiritual perspective. Life on Earth matters probably as much to the carbon system as the physics and the chemistry alone do. The final thing I want to say is just a statistic which I use in my little book, Parents for a Future, which I think is really helpful. Guy gave you quite a lot of statistics. Hopefully you took them all in, but some of them are hard to kind of comprehend. Here's one which I think really helps to understand the scale of the problem that does come from fossil fuels. If you know the answer to this, don't shout it out. So when we burn fossil fuels, we create heat, right? And we also release carbon. What do you think is the ratio between those two in terms of the effect that they have? So in other words, do you think that the amount of additional heat that gets trapped in the atmosphere in the way that Guy described from the carbon that gets released, do you think it's like the same as the amount of heat that just comes straight out from the burning? Or do you think it's 10 times as much? Or what? Does everyone understand the question?
Not really. You mean like how much do we have heat effect
Yes.
from a specific amount of carbon?
From the specific amount of heat that gets released from the actual burning,
Yeah.
versus how much heat gets trapped as a result of the carbon that's released from that same burning, as a result of there being additional CO2 molecules in the way that Guy described that then traps the heat.
It is multiplied.
Yeah, exactly. How much does it get multiplied by? Anyone want to guess?
Depends on what you're burning.
It does depend on what you're burning. Let's say you're burning oil. How much would it be in the case of oil? It would be more in the case of coal.
I'm not sure what the heat efficiency ratio is.
Go on. Someone have a guess.
I don't know,
I'll have a guess.
Yeah.
I know.
Why you know?
Well, actually, I know that I don't know the answer, but I know that it's a lot.
Yeah.
Right, so I think
So
in
take
order
a
of
guess, go on.
3,600 times
Yeah. It's about 60,000.
60,000.
Oh, I would have said
60,000.
100.
Yeah, me too.
Most people say 2 or 10.
So one match, 60,000 matches.
Yeah, that's right. That's the way to think about it.
The
So
main-
the
that-
heat,
but
you
one
strike a
match.
match,
Ah,
feel the heat
60,000.
from that. Actually, you've created 60,000 times as much heat as that over the next 100 whatever years.
Oh,
Found.
my.
And that really doesn't that bring it home? Doesn't that bring home? I mean, it also it does kind of make you think a bit more about your personal
Makes you look
responsibility,
sick.
right? Yeah, it makes you sick. I mean, because obviously the real point here is in terms of public policy and jet planes and so on, but also just like all right, so I put the cooker on and I create some heat, and I think, yeah, I'm contributing a bit to the problem. You're contributing 60,000 times as much.
Oh dear, this is.
That's about the figure. The actual figure is about the same for fossil gas, by the way, as it is for oil. Once you take into account the methane that gets given off because of the way that climate
But I
is.
hope we will come back to the personal responsibility, but because I feel it would be a trap.
Yeah,
That's
absolutely.
where people
I don't want to go.
in anxiety,
Yeah.
and then the joy is gone, and then they can't go in the transformative.
Absolutely. I don't want to go too far down there. I'm just saying
Like
it
awareness.
kind of it makes you think about every little bit a bit
That's it.
more.
Awareness.
Yeah. There you go, folks. That's where we are.
So I'm going to add one, when you're talking about the whales that we've destroyed, the fish. Right now in British Columbia, where I live, we're destroying forests to the so rapidly that they have, instead of being a carbon sink, they are now emitting more.
Yeah.
That's what our forests in British Columbia have.
And it looks
done.
like we've reached the
Changed.
same point in the Amazon as well, which is really terrifying.
Yeah, but BC was like the Amazon, and it used to sequester more.
Yeah, and that's a really good point. So I talked about basically the emission of greenhouse gas from fossil fuels, but the other thing, of course, that is happening is that the natural places that the CO2 falls out of the sky, which is such as these forests that absorb more than they release, they're called sinks, as per the whales. So the phytoplankton grow, pull the carbon in, the whales eat the phytoplankton, whale dies, takes the carbon to the seafloor. The sinks are failing as well.
Yeah.
So not only are we adding up, we're also reducing the size of the plug in the bathtub, if you like.
We haven't even talked about loops. You know?
Yes, we haven't really got into the feedback loops and the virtuous ones and the vicious ones, and the fact that there's rather more vicious ones than virtuous ones. That would take quite a while longer, I think. But yeah, it's pretty serious.
Are we going to go through some of the adaptation things you've been looking at during the weeks? Or?
Well, so next week we'll talk about adaptation mainly from the perspective of what does something like transformative adaptation mean in terms of human systems, in terms of human beings. So yeah, what I call spiritual adaptation, also deep adaptation.
Yeah, thank you very much. And it's a lot to take, but basically, from my perspective, it's like we're fucked. And at the same time, I have this feeling from you put it like kind of a system, and we have a big understanding. But I wonder if you could even had. You were mentioning some scenarios, like like visually, like we're talking now about decades. We're talking about the acid ocean, because I feel like for the mainstream people like me, that's what we're missing. At one point, when we put our head and make the effort with the right people, and it's already difficult to find them, so I'm very grateful for you to be here. But it's still, I don't have a movie in front of my
Yeah, absolutely.
In some way, I need a movie to
So I strongly agree with that, which is one reason why I'm now working with dramatists and filmmakers, which I think could be really important. I think there needs to be a lot more than that. Let's not try and give you any scenarios about involving feedbacks, because that would require more background. But you can have some kind of credible future scenarios which don't even involve feedback. So if we carry on something like the way we are, and if we make some efforts to improve things, then it still becomes more probable with each passing year for a long time into the future that we experience multi-breadbasket failure. And multi-breadbasket failure basically means that there isn't enough food because the world's breadbaskets fail. We're probably going to experience a little bit of that this year with the Ukraine crisis, because Ukraine is one of the world's breadbaskets, and so is part of Russia. Both are going to perform well below average, even if the weather this year is relatively benign, which it probably won't be. So we may experience a bit of that, which could actually be a good thing in the sense it could be a kind of shot across people's bows, although obviously there'll be some very unpleasant suffering along the way, and the suffering is already happening now. I mean, you've seen food prices shoot up already, right? So there are various kind of possible futures that scare me a lot. Some of them involve vicious feedbacks, but the one which scares me the most still, and which doesn't need to involve any vicious feedbacks, is simply that. It's simply that in 15 years' time, 20 years' time, we experience a multi-breadbasket failure event as a result of unprecedented weather chaos across the world. That means that very large numbers of people starve, and if that happens, there will be untold effects in terms of war, migration, etc., you name it.
Regarding what you're saying, it's like it's pretty sure. So why do we continue to say if we wouldn't match blah blah blah? Because that, for me, it's dissonant. I still, and I understand why we want to believe, but there is this. If we don't do that, we might end. And from what you both told us, that's it. You know, let's face it. We won't match 80% of what we should do. So,
except it's always more complicated than that, right? The ultimate reason why it's more complicated, and again we'll be looking at this next week, is you say, well, it looks like we're fucked, right? And I'm kind of inclined to agree with you, but then it doesn't stop there, right? We have to decide what to do in response to the fuckedness.
exactly.
And one thing we might choose to do is to engage in big projects of deep adaptation, right? Another thing we might choose to do is engage in projects of rebellion. Now, these projects, are they likely to succeed? Well, probably not particularly likely, objectively speaking, but we're in an unprecedented situation, and people are going to respond in unprecedented ways, including very deep ways. So, the beauty of the situation is that we actually always have the capacity to respond with our consciousness and the fullness of our being, politically, but also much more than politically, to any and all of these things, including these kind of really shocking realizations. So that's why it seems to me that it's the way that the collapsologists, some of my colleagues here in France put it, is basically they say, look, we're fucked, but hang on, the fact that we recognize that we're fucked means that it's not actually 100% clear that we are fucked.
Yeah, no, totally agree. I just wanted to say on the fact that we will have a food scarcity. If we don't integrate that, we won't be able to get in the solution of adaptation. If we still believe that we will be okay with food, that's what I wanted to say.
Okay, good.
On the artificial, we need to integrate the artificial, and right now, most of people don't realize that we will have a lack of food. They don't realize that we might have billions, trillions of people moving in Europe.
Well, not trillions, but...
No, well, I don't know. And I don't know the figures. So exactly, I totally agree. Unless we don't integrate that, we won't be able to see that it's an opportunity. But I totally agree.
And the migration one, I think, is important because we are still pretending, that it's just moving from one country to another. Oh, this country to here. No, it's global.
Yes, and as well as the fact that, something which is going to happen in quite a sure way over the 21st century, unless we are very determined and very fortunate, it's pretty much certain that gradually the parts of the world that are uninhabitable will expand,
Yeah.
and the parts of the world that are barely habitable will expand. Now, right now, there aren't that many parts of the world that are uninhabitable for human beings, but there will be almost certainly, increasingly during this century, places where it is basically fatal to live unless you live in an artificially controlled environment, which of course is enormously resource intensive to do. Like when I went to Dubai, to the biggest shopping mall in the world, they have a ski slope there. It's completely insane. Just imagine the energy that takes when it's 40 degrees centigrade outside. What's that?
Ashamedly have been on it.
Yeah, you've been on it. It's brilliant. Okay, presumably that was in her former life. So just finish that point. This is pretty much sure. You can kind of draw a line. You can draw maps of these areas that are expanding. Well, look at the way that kind of feeds into the scale of the migration issue.
That's what I'm talking
I was
about.
googling that just then with the equatorial line of population in that zone.
And people have no idea how that's going to affect them in North America with people pushing for all the resources,
Build a wall.
the whole world.
One of the concerns is this concept called wet bulb 35. So wet bulb 35 is showing up more and more as this like, whoa, this is how people die from this heating.
What's it called?
Wet bulb 35. So dry bulb and wet bulb is temperature differences that meteorologists use. So wet bulb sort of takes account temperature plus humidity.
Which is much worse than just dry heat.
Absolutely. I used to work in physical work in digging up service stations back in Perth. It got to 46 Celsius one day. Fine.
Dubai gets a 50 with 95% humidity.
Well, that's with the humidity, you can't sweat. So if you're in an environment where it's 35 degrees Celsius and 100% humidity, you will die in the space of a few hours.
Because you can't reduce your heat, because sweating doesn't work anymore.
So if it's a higher temperature but a lower humidity, it sort of follows this wet bulb 35 line. And one of the reports that I saw, science papers, was saying that by 2070, large portions of China's agricultural regions are going to be routinely suffering these conditions, which means men working out in the fields are going to drop dead, or that you're just not going to be able to properly function.
Too much
I didn't know
humidity.
that.
Huh?
Too much humidity.
Yes.
Temperature increase and all of the irrigation creates the humidity.
Oh, right.
Yeah, the food bowl.
Ah.
Yeah, and they're already starting to see pockets of wet bulb 35 temperatures pop up. There's a little bit in Iran.
This is the scenario in Kim Stanley Robinson's novel, Ministry for the Future, which is quite interesting because it creates a kind of scenario.
There's 20 million Indians that
Yeah,
die.
it imagines a serious wet bulb event where 20 million Indians die, and this sort of
Over a weekend.
wakes the world up. And they do solar radiation management, and loads and loads of other things happen, and we sort of make it through. In my opinion, the book is actually seriously over-optimistic, but it is an interesting attempt to think about what the future might be like and to include some positive dimensions to that thinking.
One other thing I just wanted to comment on is that we humans, since the Industrial Revolution, prior to the Industrial Revolution, we had not tampered with the climate system and the greenhouse gases to any noticeable amount. You could actually trace increased methane in the atmosphere back probably 15,000 years to the beginning of thousands of years anyway, to paddy fields and so forth. But in terms of actually mucking up the system, breaking it, that's something that's contemporary. But what I wanted to say was, and this comes back to Gaia Theory. Gaia Theory is this idea that the planet's temperature regulation through the control of the greenhouse gases was actually a function performed by nature automatically. And to one of the core elements of that is the phytoplankton, the plankton in the ocean. So the plankton in the ocean absorb the CO2, and if there's a lot more of them, they're absorbing more CO2, and if there's less of them, they absorb less. But they also produce this molecule called dimethyl sulfide, DMS, which breaks apart in the air to release sulfides, which reflect sunlight, which is this albedo effect. And so the plankton are actually a mechanism by which nature regulates the temperature of the planet so that it is most suited to the life that is living on the planet at the time. It's absolutely gorgeous. And And then again, this comes back to, for me, the eco-spiritual thing is that this planet's looking after itself, and we've come along and broken it. And the concern is that if we break it too much with climate change and too much heat, that we will degrade it to such a point that it could take a very, very, very long time before it can re-establish its balance, and then
Yes.
the beautiful.
Which is what Lovelock discusses in his recent work.
Right.
I guess that's a sort of beginning of an advert for your session tomorrow.
Yeah.
We should probably finish off very soon, to be honest, like over what we said. Just one slight point of disagreement. I think that there is reasonably good reason to believe that actually we did accidentally mess things up quite badly quite a lot longer ago.
Okay.
I'm thinking, for example, of the destruction of the megafauna.
Right.
In other words, that in every continent except Africa, the really large land animals have all died out, and there's controversy about why, but it does seem as though there's reasonably good evidence to believe that quite a lot of those extinctions, at least, were precipitated by human hunting, etc. And this has had dramatic consequences in some cases, including massive loss of tree cover, for example. And if you have a massive loss of tree cover, then it means that loads of carbon's going to the atmosphere. And sometimes it kind of flips around, like they reckon that the invasion from Europe of the Americas caused so much death among indigenous people that there was a huge recovery of forest cover, which absorbed a load of carbon, which precipitated the so-called Little Ice Age. So it's amazing how things which we think of as just kind of purely human phenomena can have these kind of knock-on effects. But anyway, the point I was wanting to make was there is reasonably good reason to believe that, for example, in Australasia, human beings have been instrumental in the destruction of the megafauna, which led to a new fire ecology, which destroyed vast amounts of forest cover.
Okay.
So, for example, this is in Tim Flannery's incredible book, The Future Eaters. Isn't that a great title?
Yeah.
The Future Eaters. That's us, folks, in case you haven't worked it out. And Flannery's got this fascinating idea. Maybe this would be a nice idea to end with, because it sort of keys you up for tomorrow and feeds back into what we're doing in general in this residency. Flannery says, okay, so if it's true that lots of our predecessors demolished the megafauna and destroyed their ecosystems, but if it's also true that when we look at indigenous people today, they seem in the vast majority of cases to be really kind of profoundly aligned with and in harmony with their ecosystems. Well, how do we square this? Seems like a paradox, it seems like a contradiction. And his proposed answer basically is that they learned.
The hard way.
The hard way, and the ones that didn't are not here anymore. And his thought then is, well, we need to learn from them to avoid making the same mistake again, because if you make the same mistake again, then there isn't going to be any recovery potentially. There isn't going to be more chance for future learning.
Where would you go about finding the stats for migration statistics? Because I know that would terrify most Western cultures.
Yeah, of course you need to be a little bit careful with that. But
it would literally be building walls everywhere.
Yeah. Or you could, of course, approach it in a more way of enlightening self-interest and say, hey, how about if you solve the problem and help the people who are living there to be able to carry on living there?
Well, they'd rather be, right?
But sometimes you need to scare the shit out of people for them to look that way.
No.
Yeah, but you need to think carefully about how you do that and where you're going with it.
The indigenous that you refer to in the future readers, in British Columbia we have an inordinate number we have a large number of indigenous people. And so it's helped us to be aware of exactly what you're saying, but not in a book. In reality, they have solutions.
Yes, absolutely.
And we do not listen to them.
Yeah, no, I mean, really what Flannery is saying is that's what we need to do. We need to listen to them, not just read his book. Yeah, but it's a lovely way of making the argument and bringing the gravity of it home, I think, that if we don't learn from indigenous people, etc., then we will probably go the same way as the indigenous people who didn't make it and destroyed where they lived, but it'll be a lot worse. Thanks, folks. That seemed to work. Great.
Thank you.
Yeah, thank you.
Yeah.
Mm.
Okay, thanks.
Oh, that's very good.
And I'll let you all know on the WhatsApp maybe at the weekend or early next week what's going on with the working group 3.